Hi, in this video we're going to talk about conservation momentum, but in particular we're going to talk about what exactly is conservation momentum good for? Why would I use conservation momentum? When would I not want to use it? When might another tool be a little bit better to analyze a particular situation? So a little admin note, notice that I am going to be using COM for conservation momentum as I write, because that's just a whole lot easier. So let's get to this question of what is conservation momentum good for? Well, let's talk about what might be in your physics toolbox. Now, we have many tools in this physics toolbox that we've developed. We have our Newton's law of gravity, we have our motion equations, we've got our circular motion, acceleration. But the three main tools that I want to think about now are, number one, Newton's second law and all the motion equations that could be used along with that. I want you to think about our impulse momentum theorem. That's a lot of words, so let's instead just write J equals delta P. And then the last one I want to think about is conservation of momentum. And really, the way I want you to think about it is this is our order of priority in use. So in other words, conservation of momentum would be like the third tool that you would consider using in analyzing a situation. Newton's second law would always be number one. Then, if Newton's second law isn't available, you're going to ask yourself, well, what about the impulse momentum theorem? Is that available? And if that's not available, then, hey, what about conservation of momentum? Can I use conservation of momentum? So let's go through those real quick. What would be a Newton's second law kind of problem in which you would want to use this tool? And of course, we've been over this, but just to remind yourself, suppose that we have a cart and it can roll without friction, and you've got a constant 10 Newton force pushing on it, and the mass of the cart is 2 kilograms. This is completely a Newton's second law setup, and the reason we know that is because the force is constant, and that means we can just say, hey, acceleration is force over mass, and we can get the acceleration is going to be 10 newtons divided by 2 kilograms, or 5 meters per second squared. And then we can use that information, assuming we know the initial velocity, we know the initial position. We can at all times say, where's it going to be in the future? What will be its velocity at any given time in the future? How far will it have gone at any point in the future? This is not a conservation of momentum problem. Okay, this is where a pure Newton's second law problem. Okay. What about a situation where we've got something like a golf ball and it's on a tee, and you've got this big golf club coming in and getting ready to smack it? And what kind of a problem would this be? Well, suppose that you also, I'm not sure exactly how you would know this, but suppose that somehow you got a force versus time profile of this interaction between the golf club and the golf ball, and you knew that the impulse on the club was 500 Newton seconds. Is this a Newton's second law problem? No. Okay. Newton's second law, can I use that? And the answer is no, you cannot, and hopefully you can see why. Is Newton's second law problems only work when the force is constant. Here we have a force that at the moment of impact starts out at 0, rises quickly to some peak value, and then decreases again. So we can't use Newton's second law. So then we go to our toolbox and we say, oh, can we use the impulse momentum theorem to maybe make some predictions about what's going to be happening? And the answer, of course, is yes. So let's think about that. Impulse changes momentum, and for constant mass, That would be change in momentum would be mass times change in velocity. So here we got to make up let's just make up 0.1 kilogram. I don't think a golf ball is actually that massive, but let's just pretend that it is. So here, what can I get out of that? Okay, I know the mass, I know the impulse. I can predict the future velocity of this thing, and let's assume, like in most golf shots, that the initial velocity is 0 there. So I can predict that delta V is going to be equal to whatever the impulse is divided by the ball's mass. Here the impulse was 500 Newton seconds, and the mass was 0.1 kilograms. Wow, that is going to be going... That may not be totally realistic, but that doesn't matter. This is just an example, because that's going 5,000 meters per second. I wish I could hit a golf ball that far. I should say I wish I could hit a golf ball that fast. That's like 12,000 miles an hour. So something is not realistic there. Now, I can know the final velocity of this golf ball as it goes screaming away. But what can't I know is I can't tell you what its future position would be at a certain time. I can't tell you what its exact velocity would be at any moment in time during the interaction. I can tell you what it would be after the collision is done. And also I can't tell you exactly how far it will have gone. But the one thing I can tell you is what the post-collision, post-impact, post-smacking velocity will be. So we give up some things when our force isn't constant. We lose some visibility, but we can still answer something. We can say, hey, given this impulse and given the mass, I can tell you exactly how fast the ball will be going after the impact. Okay, so now let's look at our third tool, conservation momentum. And let's look at an example where, hey, conservation momentum would apply. So this would be a scenario where, suppose that we had, let me move that up. Suppose that we had, the classic case is, and you'll be looking at these cases, is we have two rail cars. And it doesn't really matter right now, but typically we're going to call one 1 and the other one 2, and this guy number 1 is moving at 5 meters per second. The second rail car is not moving initially, and let's suppose the masses are known, that this is 10,000 kilograms and this is 15,000 kilograms. And we can see that since 1 is moving and 2 isn't, that there's going to be a collision at some point, and 2 is going to smack into number 1, and let's suppose that they join together, as rail cars tend to do when they smack into each other. And so we have these kind of joined rail cars, and they go off together to the right, and I want to know what would be the velocity of those two rail cars moving off as they get stuck together. Could we use Newton's second law for this? And the answer, of course, is no way. We don't know anything about force. We know that there is a force. One's going to be pushing on number 2, causing it to move, etc. But we don't know anything about that force, and it's not constant. What about the impulse momentum theorem? Oh my goodness, why am I writing this up? What about this guy right here, the impulse momentum theorem? And the answer again is no way. We have no info about force, either it's not a constant force, and we don't know anything about it. We don't have the impulse. This is exactly the situation that conservation momentum is used for. Okay, and that's exactly why we're going to use it. Okay, in these situations. So we use conservation momentum analysis when Newton's second law isn't available because either the force isn't known or it's changing. We use conservation momentum when the impulse momentum theorem isn't available because we don't know what the impulse is. We don't And so this is what we're going to be looking at in the next several videos, and what you're going to look at in your textbook, etc. This is the situation for conservation momentum, and there's many other similar ones, and so that's what we're going to do.